Morning everyone, my name is Leo Udeji, and today I'll be describing how my spiking neural network implementation works. Let's go over the goal of this project. So the first goal was to have a high level implementation of my design, and then we moved to the OpenMP implementation, which is meant to find the bottlenecks and see how we can optimize the code. And then finally, which is the goal of our design, is to optimize the project on the FPGA device and find out how many FPGA resources, especially DSP blocks, will be used. So let's go straight to the spiky neural network. So I'll try to explain this picture, which is a bit symbolic of what I have designed so far. So my spiky neural network has three layers. It has the input layer, which here is described as a sensory layer. It has a hidden layer where most of the computation is done, and it has the output layer. So the spiky neural network is a bit different from the convolutional neural network, which is widely used, because the spiky neural network implements certain features like lateral inversion. No, not lateral inversion. It implements lateral inhibition. It implements thresholding, whereby the neurons don't spike unless they get to certain threshold. So in other words, it uses less resources over time. And it also learns weight. So based on learned weights, it is able to classify or reproduce the input image. So I'm basically implementing this idea in this image right here, and I followed this design flow. So I designed each component of this spiky neural network, the neuron, the receptive field. I also kind of wrote a code to create a spike train to implement thresholding and to learn the weights. And based on what the spiky neural network learns, it's able to classify our input image. So I'm using the mains data set, which is publicly available, and let me display this right here. I think I have a picture of, so in my mains data set I have the training set and I have the test set. So the training set is basically what it is. So rather than using a CSV file, I used a PNG file and have each of them written 0 1 0 1 2 3 4 5 6 7 8 9, just like the normal MNIST data set will be. But I use some sort of trick here, which I don't know if it has a side effect or not. But what I did here was that rather than implementing what they call, I think that is batch learning or something, I've forgotten the term that's used, whereby we use a certain percentage of the training set or of the data set for training, and then a small test for testing. What I did was that I used a kind of different set here for training, and I used a different set here for testing. And then I actually got those from a GitHub linking, no, not a GitHub link. I got a data set from Kaggle. I think I was able to find somewhere where someone had already uploaded all the sets, so that's where I got my images from. So let's go into describing a bit of my spiky neural network. So let's assume that this is a neuron, and then each neuron gets inputs to it, and each of these inputs contributes to the potential of the neuron, and the neuron keeps record of how much each of these inputs contributes, and then at some point the neuron spikes. So when it gets to or gets above a threshold, it spikes and sends this signal to the next layer, and it also keeps a record of the input that made it spike and sort of promotes it. So, and then that spiking also is described as firing. So when it gets to the threshold, it fires. And then if you look at this image here, this is basically a symbolic depiction of weights learning. So basically the idea here was that in my code I wrote I describe that line, that weight, as the synapse. I think I have the code. Let me show that synapse. So 3. I described that here as the synapse. So I sort of broke down every feature of the spike neural network into a separate code to make it scalable. So I started from the first one, which is making a class for all the fixed inputs, and then going slowly to describing the neuron and all of that. But then let's see. Okay, so we are done with this description. So let's go to my code, and I'll show you how this works. Let's see. Yes, so let's look at each of the descriptions. So I broke down the code into about 9 different codes, and all of them are called from a central code, which is learning underscore 9.py. So I have a total of 9 separate Python scripts, and they are all called from here. So I will show you how my code works. So I'm using the Spider IDE, and this is my previous run. So let me push that up a little bit and rerun it. So I'll show you how the code runs when I run Spider IDE, and then I'll explain to you a shortcoming of this code which I noticed. So let's see. So now it's running. Let's see. So as you can see, it's predicting among all the inputs. It quickly learns each weight, that's the synapse, and then it's predicting amongst all the inputs the one that it's currently seeing, like the one that is sent through the input at the moment, and for some reason the winner is 2. So let's see if the spiking image at the end matches the prediction. So from what I've seen so far, it's able to accurately predict 2 for most of its computation, which is kind of unique, because previously it predicted 2 zeros and 1. It goes between those 3, but also I can extend this functionality in the neuron.py to predict from 0 to 9, but I kind of shortened it to this section to make it run fast and sort of display something or prove something. So as we can see in this section, it's unable to display exactly the image that it predicted previously on this line. But when you look at my previous run, it was able to create an accurate spiking image, even though here it predicted 0 twice and had 2 multiple times. But then in this second run, it had all 2s, but then the prediction was basically noise. So one thing I noticed while running this code is kind of like on some instances when it gets 0, when it predicts 0, it sort of recreates 2 as a spiking image, which is something I'm still trying to fix. But then now I'm focused a bit more on the OpenMP implementation, because since I've been able to get this code working, it should be easier to patch the code and know it should be easier to patch the code. So now I've moved my attention mostly to the OpenMP, and then I'll look at FPGA optimization, because in future patching the code to behave as it shouldn't be too difficult. Yeah, so it's you can go to my GitHub link to see basically how I got all this implemented, but this is definitely not my final code, because I'll still have to add to all this. Yes, I'll still have to add to all these, and I'm also working on the C++ section. I don't think this is where I have it. I'm working on the C++ and the OpenMP also with Visual Studio, so definitely I'll be uploading some more code and updating what I have so far. Thank you.